Good morning, everyone.
Good morning.
All right, I'm getting weird.
Good morning.
Okay, can someone out there say something? Never mind. Good morning. Okay, good morning. All right, I'm an idiot. I had myself muted in Zoom, but I didn't have my volume off on my computer. So that was the problem. So I can quit swearing at myself now and just get myself adjusted. How is everyone this morning? Good, bad? How's the first week going? Yeah, and I almost think Zoom calling is, or Zoom classes are a little bit harder and almost more stressful than regular classes in some way, just because we're just all stressed on being stuck in front of our computers for so long doing work type stuff. I mean, we're used to doing maybe more fun type stuff, at least for hours on end. And we probably all do enough work stuff anyway in front of a computer, but now we're doing any more. Merrick, I see you still don't have your books. Remember that for this class, the one thing that you absolutely have to have is access to Alta, and you can get in there even if you don't have your book yet, or even if you don't have your access code yet. So just go in and you can click on one of those links in e-learning, like the first one, the area between curves, I think it is. If you click on that, it'll take you through the sign up process, and you can choose the 14-day complimentary access. So that should work for everybody. And yeah, is it Cassie? Is it pronounced Cassie?
Yeah.
Okay.
It's Cassie.
Okay. Yeah, lots of info to take in. It's always like that first week, and I feel like we're under extra stress this year.
Well, it's a lot of reading, not like being in class, being told what to do.
Right. So more the visual than the listening kind of thing, or working in groups on things. Yeah. Agreed. Are your classes fully online, or are you doing are they synchronous like this, or are most of them asynchronous?
All of mine are online. This is the only one that has like Zoom,
Has
like
actual
class
meetings?
time.
Okay.
Yeah.
And I wanted to do this to give everybody a chance to ask all the questions they need to ask throughout the semester. I mean, we could probably get away with fully online, but that's not what you signed up for. So I want to at least make this available to everyone who wants to be here, to at least do problems and that kind of thing. Okay, I see Nick was able to do the courtesy access. That's good. So I know that's working. Most of the publishers are really good about that for the online homework systems, that they'll do courtesy access for like 14 to 21 days at the beginning of the semester, which is really nice.
I don't know if I missed it last time. Did you show us, are there like where we can see the due dates for assignments?
So you should be able to see all those. The best place to see the due dates, there are two places. You can see my suggested due dates if you go to the schedule that's in e-learning.
Okay.
So that schedule should be in the students start here, like underneath the syllabus.
So that's like how it has like for today's date, that's something that's due today. That's not like what we're covering kind of a thing.
Well, yeah, it's kind of what we're covering and what's due today. So my thinking is that you should try those problems before today, but you probably won't finish them until after today. So it's kind of like what we're covering today, and this is where you should at least be getting started on those. You don't have to finish them. Then remember in Alta, those are the due dates that you really want to see. So if you check those, and I tried to, I got to double check, but I think I adjusted those so that, and I can do that if I need to. Let's go back to my courses. I'm going to take a quick peek at that. So I know I'm not sharing screen. I'm just taking a look at it for myself. Actually, maybe I should share the screen so you can see where that is.
Is that only available like on the e-learning website, or I was trying to figure out a way to open it into the larger.
No, it opens through e-learning. It's integrated there, and the reason for that is so that everything, just the grades from Alta, will automatically dump into e-learning then.
Okay.
there is a bit of a workaround, I think, possible if we run into too much trouble with e-learning, but I haven't had any issue with students being able to get in through e-learning, even from a phone, I think. Are you trying to get in on a computer or on a phone?
On a computer. I was just wondering to make it more full screen. Kind of a...
Oh.
I didn't play around a whole lot with it. I just kind of went into things to check it out.
Oh, okay, because it's opening inside the D2L window.
Yeah.
Yeah. And I'm not sure if you can full screen it. Okay, so like everything from this week, I put as September 9th, and I'll probably adjust those. But what I was trying to do was to take all of the lessons and put them due just before the test due date on that. Okay. And we may need to adjust those anyway. The test isn't due until like the 13th, so I'll probably adjust those. But you'll notice here on the screen that I just kind of lumped all of those due dates together, so I can push them all back at once together if we need to, and we likely will. I'm always a little bit slow getting going, and I think this semester has its special concerns. So
on e-learning,
now there are no late penalties anyway on these. So if you finish them after whatever the due date is, you'll be fine. You'll still get full credit for them.
Okay, on e-learning, at least like on mine for the like it doesn't have it set up like that, but I can click on the assignment. It says they're due back. I'm sure it's from the last class, but it's like January.
Oh, oops. Let's go back to e-learning so you can show me where that is. Let me get to, that's college algebra, so let me get to calculus and we'll take a peek. Yeah, if it says January, that is from last semester. Oh, I know what happened, I think. So you're talking here when you go content and then you look at, say, chapter 2. Yeah. So those due dates are immaterial. Okay. I should have just wiped them out. I copied the course and I forgot that I had put the due dates in there. And it's a pain to change every single one because they're all, there are so many of them. But I'll try to get in there and do that and at least adjust due dates. So due date would be, like on this one is 9/9, and then you can update. So there's one of them. I'm not going to do them all right now, but yeah. So you're right. Thank you for letting me know that. That'll go on my list. Fix the 162 due dates. And I know that it still looks a little bit different than what yours looks like, but yours should show the right due date on that first one now.
Okay. Thank you.
Is that that's where you saw those, right?
Yeah.
Okay. All right, cool. Any other questions? And I got to ask in here, is it Catlin or Caitlin?
It's Caitlin.
Okay, just double checking with the spelling.
No, you're good. Thank you.
Oh, Merrick, that's funny. You like meeting because it gets you out of work. Oh, how did you get in outside of D2L, Merrick? I'm just curious because I don't have like a course code or anything. Okay, so you signed in through D2L, but then you opened, you went to Newton.com and opened Alta from there. Okay, let me double check. Yeah, Merrick, we should just make sure that you're in there. So let's go look at who the students are. You're there, so you should be good. So you ended up, you're just going to Newton and then logging in with the account you created. And since you're in there in our class, yeah, that should be fine. And Aaron C., you did the same thing? So yeah, I think so. Who asked that? Was that Cassie asking that?
Yeah, thank you.
Okay, or Caitlin, I couldn't remember. Okay, so Cassie, try that. Try what they did. So if you've created your account, so then go to newton.com, log into your account, and then you should be able to get to our class directly there. The other benefit of having that set up that way is going to be that you can, if for some reason Delta's e-learning goes down, you can still get to Newton. So as long as you have your Newton password saved. Oh, you did access through D2L. Okay, Aaron C., thank you. Oh, gotcha, January dates. It's on my list. I'm gonna run out of room for my list on my calendar before the first week of September probably, but. Okay, any other questions that anybody ran into, maybe calculus-wise starting out? I'm gonna do a couple reminder problems on areas, and then we'll do some other stuff. Oh, Cave's here. So, all right, I'm just gonna make sure I got everything on the chat. It looks like I do. Okay, so is everybody feeling pretty good about being able to access things in Newton? You just want to just maybe go over any questions for anyone on the review that I put out there, the 161 material review, derivatives and integrals. I did get that posted, but not until this morning. So all of those solutions are there now, and you should be able to get to them. No, you're good? All right. What about any questions?
Sorry about that.
Sure, go ahead.
What'd you ask? It was still connected for me.
No, Curtis, the solutions to the review sheet that I sent you guys last time, and if anybody missed that, I also uploaded the review sheet itself. They're in D2L. So they're under, I think where I put them. They are in the introductory materials down to the bottom. It says Calculus 1 Review and Solutions.
Okay, thank you.
So, and I put the original document up there as both Word and PDF. And then I put the solution key as PDF.
Okay.
So you can.
Yesterday's Zoom meeting, what did we cover?
What'd you say?
I missed Monday's Zoom meeting. What did we cover?
So mostly we overviewed the system. We went through the syllabus, and we went through like how to get into Alta and showed the Alta system. And then we really didn't do any problems other than just kind of flipping through the Alta problems to show how that worked.
Okay. Did we start lectures today?
So yeah, and I'm not going to lecture a ton. I'm mostly going to answer you guys' questions. But today I figured maybe a lot of people wouldn't have questions. So I do have a backup plan with some problems that we can try that are going to relate to what you're going to see in the first few sections in Newton.
Okay, and is it review in Newton?
The review is right in e-learning.
Okay.
So if I'm gonna
Cool.
go back here and I'll share my screen again. So this is e-learning. If you go to content and then to introductory materials, and then you can scroll down to the bottom. And there's a nice little intro to Newton video there you can check out. It's short, it's only less than 3 minutes, so it doesn't take too long. There's a link to the OpenStax textbook, so you can link there. A formula sheet, I threw that up there for everybody. The review is not for a grade, that's correct, Aaron. And then there's the review. I think it's got like 10 differentiation problems and 10 integration problems. And then the solution is linked. So it's just like a worksheet kind of review thing.
Okay, thank you.
Okay, yeah. And then, so today let's jump over. Just want to make sure that I'm not missing. Anything. Just in case anyone is looking back, I'll throw the chat up there. Okay, so let's jump over to some practice problems. This course is kind of set up. Let's see, myself unsharing screen. This course is kind of set up with essentially 4 units. So that we're going to start with some applications of integration, and then we'll move into some integration techniques. Some Calc 2 classes reverse those 2 chapters, and it doesn't really matter which order you do them in. If they do the techniques first, then they can give you different problems in the applications. So it doesn't really matter what order we do those in. It's just sort of maybe professor preference. So we're going to do the applications first, then the techniques. Then we'll do the sequences and series unit, which is maybe a little bit different than stuff that you've seen in calculus or in other classes before. So you might have done a little bit of sequences and series in your pre-calc class as an intro to that, but we'll start that semi from scratch. And then we'll go on to polar and parametric curves. And again, you probably saw a little bit of polar parametric in maybe a trig class or a pre-calc class. So that's sort of the outline of the class. And we're going to start today with our, let me think. And I'm actually going to turn on video here, which is a little crazy, and stop video here. So I'm kind of backward now, but that's okay.
Can I ask you a question real quick?
Sure, go ahead.
So what should we already have done or completed by now?
All of chapters 2, 3, and 4. Anybody panic there? I'm just kidding.
Yeah, I hoped you were kidding for a second. I really did.
For a second.
Really right now, where you should be is you should have just at least started the area and volume chapter. So the first couple lessons in chapter 2.
So if I haven't done that,
and you're
then I
going to
should
want to
probably
start
do that.
kind of zooming through and maybe seeing what you can get done and how long they take. And so you can kind of balance yourself and figure out, how much time you need to devote. I think part of the biggest issue at the beginning is just sorting out how long you need to work on each lesson. And you'll get a better idea of that as we move along. And you'll also probably get faster at it as we move along. It's always hard learning a new sort of homework system. If you've used My Math Lab before, a lot of people have, you get used to it and then it gets a little easier. I think this one kind of gets easier faster because they show you how to do things even if you do them right. So they always provide the solution to the problem, even if you happen to get it correct, and you might see a different solution than the one you used, which is always good. So yeah, you should just have started on, say, the first couple of assignments right now.
And those assignments are on the that one website, right?
They are, you can go get them after you've logged in through D2L. You could get them directly at newton.com, or you can just get them right in eLearning. So all of those, let me go back to my screen share. All of those are in here on our eLearning site. When you get into content and click on any chapter, so let's say we click on chapter 2A, that's our first chapter. The first assignment is finding the area of a region bounded by two curves. So if you click on that, it's going to take us into that assignment. And it's going to give us problems. And preview will give it to me in sort of the same view that you get.
Okay, do we have to the unlock button?
You'll get a little bar up here that shows how much you've mastered the assignment.
Okay, because for me it says I have to unlock.
Okay, so did you register for Newton yet?
No, I do not think I did.
So that's what you need to do. This is Chris, right?
This is Gabe.
Oh, sorry, Gabe. Okay. Or sorry, Chris. I don't know, whichever way. Okay, so yeah, and we can work through that later together if you're still struggling with getting that unlocked, but you should. So when you click on that and it's not there.
Yeah, it's there, but it just says unlock. It says like unlock, and then it shows objectives and stuff. And it says, yeah. It says I need the an access code to access your Newton course, and then purchase. Okay,
so click, but you can do so you do need to purchase the access code. But in the meantime, you can do the 14-day trial.
How much should I get for the access code? How much should I pay for that? The $9.95 or the $3.99?
So the $9.95 is only for a month. So if you do that, you're going to have to keep re-upping. I mean, it's fine to do that. You just would have to do it 4 times. It's funny that it's actually a little bit cheaper to do the 1 month at a time. But you can do, if you want to do the complimentary access for 2 weeks, then you have to do either the $39.95 or the $79.95. I mean, I would recommend the $39.95. That gets you for the whole class, and then you only have to do that once.
Yeah, awesome. I do.
You know what I mean? Then you don't have to be messing with it every 4 weeks.
And I should get the courtesy access, you said?
You could do courtesy access right now if you don't want to pay for it.
Oh,
if you don't,
is it just for 14-day trial?
Yes.
Okay.
So yeah, and then you can go in once you purchase the access code at a later date, you can go in and put that access code in, and then it won't be the courtesy access anymore.
Okay.
But
so
it will all work the same.
Okay, it'll create an account for me automatically, or like
you're gonna have to go in and
buy one, right?
When you click the courtesy access, it's gonna ask you for all that info for your account.
Okay, cool. Thank you.
You're welcome. Okay, I'm gonna kill that share and let's see. All right, so you know what, let's, I should actually go back there and share that again, because let's go in there and find one of those questions. We glanced at one of those yesterday, but we didn't do it. Remember, we just did the instructor cheat, or maybe we did the wrong answer intentionally. I can't remember. So here's a problem, and you guys should be able to see this, right? Calculate the area in square units bounded by two curves over the interval from -8 to -6, and it says do not round, enter an exact answer. So they're pretty good about this. They're going to tell you do not round, or round to 2 decimal places, or round to 3 decimal places. So pay close attention to those so that you're not messing up by maybe giving them a decimal answer when they want a fractional answer. So let's just take a minute and get our calculus brains going again. and think about how you would do this. My suggestion as you're moving into this is to sketch a graph. Sort of always my suggestion. You can use any graphing calculator you have. You can use Desmos. You can, what else could we do? You could use Mathematica, which I'll show you in a minute. I did get that sorted out since last time. Yes, Desmos does work great for these. Erin is right. It's probably the easiest in terms of, you know, there's really no learning curve to Desmos. You could just go in and use it. And the nice thing is how it shows intersection points. So I'm gonna Desmos myself over here. And I think actually I'll just jump out on my iPad. So yeah, the other one is sharing. So I should be okay there. So I'm just gonna jump out. If I lose the meeting, I'll come back in later. And I might be able to hopefully flip the share. So in Desmos, I'm going to graph my two equations. So y equals 3x minus 47 and y equals, and you don't even have to do the y equals, x squared plus 17x plus 1 minus 1 plus 1. And then I'll get a decent window. And they even told us over the region -8 to -6, which is kind of interesting. So I'm actually gonna take myself back to Zoom and I'm gonna stop my share here and I'm going to start my share here. All right, so there is Desmos. I just did that in the Desmos app on my iPad. You can do it at desmos.com, so any device. And you'll notice that this is why this is nice and easy. I can just tap on those and locate key points. So for example, those are 3 key points on the curves. The -8.5, -71.25 is the vertex. The -8, -71, and -6, -65 are the intersection points. So that's why it's really nice when you have Desmos, because you can really quickly and easily get those intersection points just by, and I especially love it on a touchscreen device because you can just tap them and then you've got those intersection points that you're going to need for the integral that you set up. So looking at those, we're looking for the area between the curves on the interval from -8 to -71. So that's just that little wedge between the two curves. And which one of those graphs is above the other one, the line or the parabola?
Well, they're both going to infinity, so how would we know?
So, but between, so from -8 to -6, so let's zoom in even further so we can look at this a little bit bigger. In that, so if I'm thinking of shading in between there, so the region I'm looking at is below the purple line and above the black parabola. Does that make sense?
So it's in between those 2 points?
In between those 2 points. Let's go back.
Can you show it with your cursor possibly?
So yeah, can I?
I
can. So can you see where I am right now?
Yeah, yeah.
You can see that. Okay, so that's the purple line.
Right, so it's the right of that? Okay.
So from here to here, from -8 to -6, below the purple line and above, actually I can show it. So right in this region, this stuff in here.
Cool, thank you.
That part. And if we go back and actually look at that problem again. So you guys have that graph in your brain, right? I'm gonna switch back over here. to, yeah, I'm going to switch back to my screen. And notice that it says bounded by. So those are the boundary lines for the two curves. Those are the boundary lines. And over the interval from -8 to -6. So, and those, since those were the intersection points, those are going to be my limits of integration. So I'm going to set up an integral. And what will my integral look like? Does anybody have an idea? And I'm going to actually broadcast from over here, and I'm going to go elsewhere.
Don't you want to set the two equal and then take the integral of whatever that equation is?
So, okay, so if we set them the two equal and actually solve the equation, we would come up with that -8 and -6. We would actually come up with that solution. What's going on here? Oh, here we are. We would actually come up with that solution of x equals -8 or x equals -6 that we found graphically looking at Desmos. So we really already know that solution. We know where the two curves intersect. If we needed to do that by hand, we could. We absolutely could do that by hand. But we can also use our technology to our advantage, where we've now solved that equation, where we set the two equations equal to each other. And somebody read those to me, because I've got, you guys can't see them either.
I can read them to you. I have them written down.
You got them written down. Okay.
G of x equals 3x minus 47. Oh, f of x? Okay, I can read f of x right now.
Well, I'll just throw G up here. That's fine. Or
Okay. So G of x is 3x minus 47.
okay, there's G of x. Okay,
And
and
then
f of x was?
X squared plus 17x plus 1.
Okay, and our interval was -8 to -6.
Yep.
And oops, let's undo that. Fix it. And we know from our graph that that's actually where they intersect at x equals -8 and x equals -6.
Didn't you say those were going to be our upper and lower limits of integration, though?
They are, because, and I'm gonna do a really crummy picture of what we had going on here. So we had a parabola, we had a line, and this is totally not to scale and not where these are or anything, but yeah, let's actually fix that line. So it's more like this. Okay, so at least they're both in the negative zone. So I'm just gonna label these in red. So here we have x equals -8, and there was some y value that we don't really care about. And then we had x equals -6, and again, some y value that we don't really care about. So this is back to what you were looking at in that picture. This is the area that we want to compute. And the idea that we're using, we got from back in Calc 1 with this whole idea of area between curves and Riemann sums. And now this is probably kind of tricky. How many of you took Calc 1 during winter semester when we had our great interruption?
I did.
I
You
did
did?
also.
I did
Yeah,
as well.
so all of that stuff from the end of the semester might be a little bit fuzzy. Yeah? No? No? Yeah. It's okay. All right, so, but that's the area we want. And what we figured out is that we can get the area by thinking of these as a bunch of little rectangles, and we add up the areas of the rectangles, and then we took the limit as the number of rectangles went to infinity. That was the whole idea of that Riemann sum. You guys remember that?
Yeah.
Yes, the
vaguely.
idea of the Riemann sums was
Yeah.
to find the area under the curve, right?
Yes, and it turned out when you took the limit of that Riemann sum, so the sum looked like this. You added up all of the areas of those rectangles, and the areas were the height, the rectangle height, and I'm actually just going to write the word height, times the rectangle width. And we added up all of those, like however many we had. Maybe we do 4, maybe we do 10, maybe we let n go to infinity. So we said, let's add these up from 1 to n, and then we'll take the limit. And if you do these by hand, they're a pain in the butt, and there's a whole bunch of grungy algebra in here, and you would never want to do very many of these, and some of them really can't be done by hand in this way. As long as we keep things semi-reasonable, like rational functions or polynomial functions, we could theoretically do this, but we're going to get one problem done an hour. So it's not very efficient. But if we notice, the height is just the difference in the y values. So it's the upper function minus the lower function. In this case, the height is the upper function, which is the line, g of x, minus the parabola, f of x. And the width is just the change in x. And actually, cheat this out a little bit. So the width is just that little dx, or delta x in the Riemann sum notation. But what we found was that when we took that limit, it was just an integral, right? So it's just the top function minus the bottom function over whatever our limits are. And that works in general for area. So it's upper minus lower integrating with respect to x. Oops, -8 to -6. So our answer should be integral from -8 to -6 of 3x minus 7 minus x squared plus 17x plus 1. And then they want us to give an exact answer. So, I mean, this is where several people would probably dissent on how you have to do this. I'm going to assume that in this problem, we are integrating a polynomial function, right? And you guys learned how to do that in Calc 1. Who thinks they can do this problem?
I can.
Who do you already have an answer?
I'm almost done.
Okay, cool.
Almost done integrating it. I still have to do the plug the -6 and -8 in.
All right. I'm gonna have you go ahead and work through that and get me an answer. I'm gonna switch my share so we know what we're integrating somewhere. I probably should write this on a piece of paper because as soon as I quit sharing my screen, I'm not going to be able to see it. So we're integrating 3x minus 7 minus x squared plus 17x plus 1 from -8 to -6. I think my, this, my, this, no. Okay, that's our, that one. Okay. So there's the, oh, I see what I wrote down. I wrote a 7 instead of 47. I'm right looking at this on my sheet and I'm thinking this is not going to work because that was a 47 and that will work a lot better. Who's got an answer for me? Lots of negatives, lots of ugly fractions in here, right? Actually, I'm going to stop my share. Okay. Any answers?
Almost done.
Almost there. Those fractions are messy, aren't they?
Yeah.
I think the worst part about these, minus negative 6 cubed over 3 minus 7 times negative 6 squared.
I ended up getting a fraction. I don't know if that's right.
Okay, I think there's a high likelihood that your answer will be a fraction.
So I got negative. So I got negative. Oh, if you want me to say it, I can. But
No, you go ahead and shoot. You can tell me what you got. That's fine.
I got negative 2,876 over 3.
2,876?
Over 3.
Okay, now, so my first thing is there's no way that's right.
Oh,
And the
shoot.
only reason I know that can't be right is because you gave me a negative number. And remember, we're trying to
positive,
find.
I mean positive.
Oh, okay, cool.
Yeah.
Positive, 2876 over 3. All right, I did not finish the problem. We're going to try it.
Sure. Yeah. Could be wrong.
Oh, no, it's wrong. Bummer. So you can kind of look at this and say, whoa, this is going to be a pain. Here's the thing.
Oh,
Chances are you made a sign error or a fraction error. I don't want you to miss all your calculus problems because of sign errors and fractions errors. And this, like most online homework problems, does not really try to give you very nice numbers all the time. So, I mean, this could have been way worse. Our limits could have been fractions or something like that. But still, it's not necessarily very easy to work with all those when we're trying to get the concept of the area between the curves and we get muddled in the signs and the fractions and the whatnot. So I'm going to encourage you to use technology if you want to go ahead and evaluate those integrals, or at least to do the calculation part in the last step. So if you want to grab a calculator to do that part where you plugged in the -6 and the -8, you can do that. If you want to use technology like, say, a TI-89 or an Inspire CAS or Mathematica or Wolfram Alpha to do those calculations, you can do that. So here's going to be my thing on technology. If the problem is about and an integration technique, then I'm going to ask you to use that integration technique and not use technology to compute the integral. But if the problem is about an application, like in this case where it's area between curves, once you've set up that integral that you need, I'm cool with you going out and saying, okay, I'm going to go ahead and let the technology help me integrate this function and evaluate the integral. Does that make sense?
Yeah.
Okay, Curtis got
Yeah.
584/3. We're gonna trust that? Yeah, let's try again. Let's see, 584/3. Oh, let's see. Oh, it was 4/3. Huh. All
you
right,
got,
so there's the piece that we just did algebraic or graphically. They did algebraically. They found the intersection points. They integrated the difference of the functions. This is the integral we had set up. That's what I had. I went all the way to here. They noticed they didn't even show us their work. They just said, this is it, and that equals 4/3. So they're not showing us the work on the algebra of plugging in those numbers.
yeah, I got
So remember,
3x minus 7 for my g of x, not 3x minus 47. Not 3x minus 47.
yeah, you know what? That was my fault. I wrote it down wrong at first, and then I sneaked my 47 in there.
Yeah.
Yeah, that was me. Sorry.
No,
And
it's okay.
that's why it might have actually, no, that would have made it positive because that would have been further up. That's why your number was so big, because that line would have been much higher, right? And there would have been a lot more area between them.
Would have been positive instead of negative. That first one, yeah.
So yeah, so but you can kind of see now how that works. We should have had that correct. Now, there are lots of ways to get this. The other day, we were talking about getting into Mathematica when we got waylaid because I couldn't get into it, and we just cut it off there. So I'm going to show you Mathematica today, which is great for doing lots of things. It's not great necessarily in the learning curve area, but it's an extremely powerful computer algebra system. So you can do lots of checking of your integration here, which is really nice. You can save your work here. Maybe it's a little bit more complicated getting started than on a calculator, but it's going to be much more powerful than, say, a TI-89. I think that I put the link to Mathematica on our announcement page. That link should have opened today. If it didn't open, it opens right after class today. But let me give you a quick oh, and it's working now. I actually probably should show you elsewhere so you can see how to get started. If you download the link, it will ask you to install. So it does have to be installed on a computer. It can't be installed on a tablet. There are some workarounds and there are some other things that you can use, but this is really quite nice. And we're going to sort of enter some inputs, and I'm going to just go ahead and use Wolfram language. So we're going to first enter our functions. And what were our functions? They were g of x and f of x.
You want me to read them off to you again?
Yeah, let's get them. We'll get them right this time. Let's see if we can do this. This is probably going to seem a little bit daunting at first, but I'll share this out with you so you can see how this works. So function g
is 3x minus 47. 47.
Okay, so syntax is a little weird.
And you're
3x minus 47.
Yeah.
Okay. So we've just sort of defined that and noticed that they output this the opposite direction. They have a little bit different plan in terms of how they think of sort of standard form.
You want
And
to
then I could plot
right now?
that. I'm actually not going to go ahead. Well, actually, let's go ahead and plot it so we can see. It will give you some suggestions as to things that you might have wanted to do. And then f of x is x squared. What was it? Plus
17x plus 1.
plus what? 17x?
Yep. Plus 1.
Plus 1. Plus 1. Okay. Now, one thing that you might want to jot down is that every time you hit return in Mathematica, it's actually shift return. So that's a weird tweaky thing. And then I'm going to plot that. But what we really wanted to do was to plot both of those together, right? Notice as I type that you get this little info, and it gives you some different ideas of Mathematica functions that you might use. The one I want is just plain old plot, but if you want to know about it, you can just hit the info and up will pop plot info. So if I say plot a function and then x goes from x min to x max, it will just generate a plot of a function. If I want to plot several functions, then I list them in braces. So I'm going to do that. We're going to jump out of there. We're going to say plot f. Oops. And see, it's easy enough to just forget those things. F of x. No. And I'm going to share this workbook with you so that you have some examples, and g of x. And x goes from, well, we wanted -8 to -6, right? I'm going to go -10 to 0 just to get that look. And there we go. You could then solve the equation f of x equals g of x so that you came up with the solution. Let's see. Solve f of x equals, and this is kind of weird. I feel like this is not, oh, I gotta say for x, that's what's missing. And the solutions are written, x is 8, x goes to -8, x goes to -6. So we've got our solutions, those are our limits of integration. And now what did we want to do next? We wanted to integrate, right? And integrate is the function. Now, I know you guys are probably sitting here going, oh my gosh, there's so much to remember, but there are other ways to do this. So I'm just showing you the method of entering info, but I'm going to show you some other ways to get info as well. So integrate, we wanted, g was at the top, g of x minus f of x. So we define those so we can integrate g of x minus f of x as x goes from -8 to -6. And boom, 4/3. And that was the answer, right? Now there are lots of other ways that we can put info in. So one of the things that I found students like the best is the palettes. So if you go the basic math assistant, I think it has plenty in it, and it's hiding over here, so I'll pull it up. And then I'm going to go advanced on that, actually. Notice you got symbols for everything you need. So a lot of things here you can do by just a little palette. So for example, I can just choose this integral, and then it tells me enter my lower limit, -8, enter my upper limit, -6, my expression. So I could type it in with the 3x minus 7, or since I defined these, I can say g of x minus f of x, and d variable, so dx, and then shift return. Oops, what's wrong? What does it not like? That should have worked. Let's see if it just needs parentheses. Yeah. So kind of like the TI calculators, the TI-89 and the TI-92, which is a little bit older, those required lots of parentheses, and this kind of does too. So you can get that solution. Now, how many of you have used Wolfram Alpha? Anybody out there? Yes, no? Aaron E., teaching yourself integration was fun. Yeah. Aaron Comstock, you're probably even better off having a little extra time. So Wolfram Alpha, you can actually go out to it at wolframalpha.com, but you can also get it within Mathematica, because Wolfram is the company that created this program, Mathematica. So Wolfram Alpha is sort of a knowledge database where you can find all sorts of information. But if you notice at this choose how to enter input, you can do an actual Wolfram Alpha query, it's called. So it's actually going to go out to the website and it's going to use Wolfram Alpha to come up with the answer to the question. So we're going to go Wolfram Alpha, and we're going to say, we're going to try to do some of these things. The thing about Wolfram Alpha is that it's a little, maybe more forgiving. So it lets us enter things more like a human would enter things instead of in the Mathematica syntax. So I could say something like graph y equals 3x minus 47 and y equals x squared plus, sorry about that, I thought that was silenced, 17x plus 1. And no, still gotta hit it. And it sort of tells us how it's interpreting those. It wants to plot them. It plotted the two of them for us. So there we go. And we can change the minimum and maximum values of x to get a little bit different view if we want to. So it can do some adjustments. So this kind of works nicely here as well. And then we could do another one where we say, let's solve f of, let's see, I'm just going to go back to my 3x minus 47 equals x squared plus 17x plus 1. And it gave us the solutions. So it's sort of mixing inputs from Wolfram Alpha with outputs in Mathematica language, but we still get our solution. And we can even go out there and say, okay, I'm just going to tell this to integrate 3x minus 47 minus, and I do need these parentheses, x squared plus 17x plus 1 from -8 to -6. So just kind of English language, which would be how you would read that integral. And it'll do it for us. So one nice thing about doing them here in Mathematica, for me and for you, is that you can show me what you did. So you can take this workbook then and you can save it and say, okay, well, here's my work for these problems where I did them in Mathematica. And you might do them this way, sort of the Wolfram Alpha way, or you might do them this way, the Mathematica way. This actually just has Mathematica working in the background, and it's set up nicely for users in a user-friendly manner. Does that make sense? I mean, and Wolfram Alpha can do all sorts of things. Like it doesn't have to be math. You could do something like most popular boy names, United States. Okay, so Liam is at number 1 right now. Liam, Noah, William, James, and Oliver. And I don't think we have any of those in our class. You can also do something like this and say, I just want to look up my name. I'm going to look up Phoebe. And as a female given name, it's the 320th most popular for US births. It is on the rise right now, which is kind of fun. They give you a little graph of it. Here we are right now. We're way up. This is as popular as the name Phoebe pretty much has ever been. What happened along this line of time to cause the increase in all the Phoebes? Anybody know?
Probably a TV show.
Probably a TV show. And people who watch that TV show are now growing up and having kids. Pretty much. So yeah, it's kind of fun. 1,018 Phoebes per year in the US. I was born back here near the dip, the lowest area of the Phoebes. So that's kind of funny. And Phoebe was also very popular back here in about, what, 1883 or so, looks like. So, I mean, just kind of fun. Estimated current age distribution. So look at this. Most of the Phoebes are between 0 and 20. Again, that kind of fits the recent popularity. Phoebes between 20 and on out are very rare. And of course, there aren't very many between 90 and 100 because there just aren't very many people between 90 and 100. So, and then they tell you about some famous Phoebes. You can do that with your own name. So Wolfram Alpha has all sorts of information. It's not just necessarily mathy, but there's lots of data out there that they mine and can give you lots of info about. So you can use it here in Mathematica. You can also just use it at the website at wolframalpha.com. I will jot that in the chat. Oh, if I can find the chat. I have too many windows open. Let's just minimize that one. And chat, where are we? There it is. I knew it was hiding somewhere. So wolframalpha.com. There we go. So, I mean, that was maybe a little bit more time on that problem than we needed, but I wanted to show you Mathematica. I'll provide a link with the info on how you can download it in e-learning. In fact, it might already be there. I put it in. I can't remember if it was going to open this morning or if it was going to open at noon when class is over. So either way, it will be there at some point in time. All right, let's, I'm going to go ahead and stop this share. And I'm going to go back over here and start a share from this. And we're going to open, oh, where did that go? I thought it was here. No, it's not here. All right. We'll stop that because I'm going to have to find it. All right, so do you guys remember though a bit about finding areas between curves? Yes? No? Yes? I'm getting some notes. Curtis remembers area between curves. Anyone else? Caitlin says yes. Okay. Should be good. We are gonna, we're gonna do one more area problem simply because I want to make sure everybody's familiar with finding areas maybe a little bit differently. I'll just do a single note. And done. And okay.
When are your office hours, if I may ask? I know it's on the syllabus, but
Yeah, they're in the syllabus. They're before class. So 9 to 10 on Monday and Wednesday, and then 9 to 10:30 on Tuesday and Thursday. And I can do by appointment as well.
okay, perfect.
So yeah. And they'll just be in Zoom. So if for some reason you get to Zoom and you don't see me, just shoot me an email because I should be paying attention to that. I'll be sitting here and I will open the office hours Zoom meeting, but sometimes if I'm looking at 3 screens, I miss somebody popping in. So if you get to office hours and you don't see me or don't hear me, or you see me and I'm ignoring you, just go ahead and shoot me an email because I'm probably paying attention to that instead.
Okay.
All right. So we're going to go back here and I'm going to share screen again. Okay. Oops, I don't want that one yet. I want this one slightly, no. They're jumping out at me. Area practice problems. And I actually don't want those. We're going to go all the way to number 3. So this problem is asking you to find the area between 2 curves in 2 ways. And I actually want us to sort of focus on the second way, although we'll do the setup both directions. Integrating with respect to X and integrating with respect to Y. So any of these application problems, one of the things you're probably going to want to do first is just draw a picture. So this problem is a lot simpler than the last one in that we have some curves here that we pretty much know what they look like. Let's go to start. We'll see if I can do this. I am going to switch my, it should be good. My video's over there. Turn this a little bit so I can see what I'm doing. So my graph is a square root graph. So something like this, just a quick, and then a straight line, y equals x over 2. So something like this. So then we want to know where they cross. So y equals x over 2 and y equals square root of x. Okay. So this says, do this problem 2 ways. So if we did this problem just the way we did the last one, we'd say, okay, well, we want to look at those rectangles that we drew vertically. And we want to look at the top function minus the bottom function. So my integral would be, which function is on the top? The square root or the line?
Square root.
And if you guys are answering me in chat, I can't see it. Yes, the square root function. I pulled my chat up. Square root of x minus the bottom function, x over 2, with respect to x. And notice this one's going to be a lot easier to maybe not make sign errors or fraction errors or whatnot. And we want to integrate from here to here. And we can see from the graph that this is at x equals 0. And we can maybe guess at the upper limit. And if we can't, we could always go over here and say, okay, well, I want to know where x over 2 equals square root of x. So I'll square both sides. X squared over 4 equals x. And then I don't like fractions, so I'll multiply by 4. And x squared minus 4x equals 0. So x times x minus 4 equals 0. And my upper limit should be at x equals 4. And double check, yeah, that makes sense. 4, 2, 4, 2. Okay, so some nice limits of integration. And then we could integrate that function and come up with a solution. And again, application problem, if I give you one of these on a test, you can use any kind of technology you want. I think this one's not that bad. I can probably, let's see, that's x to the 1/2. So I'm going to go x to the 3/2 divided by 3/2 minus x squared over 4 from 0 to 4. Or 2/3 x to the 3/2 minus x squared over 4. So I'm going 0 to 4, and then I'm going to plug in my 4, 2/3 times 4 to the 3/2 minus 4 squared over 2. Then I'm going to plug in my 0, and I nicely get a big fat 0 when I plug in 0, so that's cool. And then 4 to the 3/2, remember, is, let's see, square root of 4 cubed. So 2 cubed is 8 times 2, 16/3 minus 2. 16/3 minus, no, minus 4. Oops. Let's erase that. Not 16/3 minus 2. 16 over 2 is, oh, I'm an idiot. I see my mistake right here. This wasn't an over 2. That was an over 4, wasn't it? So that should be minus 4. And it looks like 4/3 is the answer of the day. It's the answer again. So 4/3 square units. And that's why you check with technology, or you check a second way, or you just go back and double check your work and make sure you didn't make any mistakes. So does that problem seem fairly reasonable? Can I get a thumbs up or a yes or a something? Just,
Yes.
we're cool there. Okay, so now what is
Can you leave the
this?
work up for a second?
What'd you say?
Can you leave the work up there for a second? I'm still.
Oh yeah, and let me move the chat so you can see it. I'll just scooch the chat down here since you're seeing my screen. Actually, that chat doesn't matter. You weren't seeing that. That's on.
Oh yeah,
that was
yeah.
just a-
Right.
Gotcha. Okay, so now we're not going to leave that problem just yet. We are going to look at this other part of this part B, integrating with respect to y. So the way this works is to think about those rectangles. So I chopped this with vertical rectangles going this way. Instead, I'm going to chop my rectangles and I'm going to lay them down on their sides. I'm just going to put horizontal rectangles across this. So let's change colors so that we can see where we're working. Oops. This is what I do. I went to the wrong device. Let's go to red. And we're going to put these rectangles sideways. So, and I want to just put a little reminder in here. The width of this rectangle was dx, or a little change in x. The difference with my red rectangle is that its sort of width now is actually this little change in y. So we've switched the variable of integration by laying our rectangles on their sides. Another thing to notice, come back here to purple, this was the top function minus the bottom function, right? The function that was above minus the function that was below. For our red rectangles, it's going to be x function on the right minus the x function on the left. And our width is a dy. So we still have limits from somewhere to somewhere, but it's going to be our right function minus our left function. And we need to solve those equations, not for y like they are already, but for x. So my first equation was y equals x over 2. That was my second one. And that is x equals what? 2y. And this one I need to square, so x equals y squared. So now we should be ready to fill in our integral. Which function is on the right, the line or the parabola? Here's my
Line.
the line. And actually, where's my little pointer? The line is on the right, so that is x equals 2y. Notice I'm using x as a function of y instead of y as a function of x. Minus my x on the left is the parabola, and that is x equals y squared. Now my limits are going to change because my limits aren't x values anymore, they are y values. And y ranges from what to what in that region? 0 to 2. So notice that I get just a slightly simpler integral to deal with. I don't have to deal with the radical. So let's see, y squared minus y cubed over 3 from 0 to 2. So 2 squared minus 2 cubed over 3 minus a big 0, 4 minus 8/3, 12/3 minus 8/3 is 4/3, and we are correct. Same answer, two different ways. So that's kind of cool. Okay, so I can see both screens. Okay. How are we doing on time? Let's, I'm going to leave this area of the regions bounded by those two curves. I'm going to leave that for now. I'm actually going to leave both of these last two. I want to get to a different idea. So after area, the next thing we're going to look at is this idea of volumes. And there are lots of different ways that we can think about volumes. And one of them is in the idea of slicing. We're sort of chunking things up. And you can kind of think to the area concept. And that's sort of why they do the volumes by slicing first. When you do the areas, we're actually slicing through and looking at little slices of rectangles in our region. So with volumes by slicing, we are going to try to look at a region and come up with volumes by slicing things up and comparing to regions that we know about. So for example, let's see if I can think of something that you guys have seen that you could slice apart. If you took a pyramid with, say, a square base. If you took a pyramid with a square base and you sliced up and down, so just slices coming through, what does that pyramid look like? I mean, what do the slices look like? What's their shape? If you think about the cross sections.
Triangles.
They're triangles. And while you might not think of a triangle as a volume, if you had a triangular piece that was relatively thin, you could estimate its volume by taking the area of the triangle and multiplying it by its thickness. And its thickness would just be a little dx or a little dy. That would give you the volume for that one piece. And then you would add up all of those volumes and take the limit as n went to infinity. So this starts to look like another Riemann sum. So we're going to look at a problem that maybe is a little bit simpler than the triangle problem. We're going to start with a solid whose base is the region bounded between the curves y equals x and y equals x squared. So in other words, I'm going to make a thing, and my thing has the line y equals x, and the curve y equals x squared, I'm going to kind of emphasize it a little bit curvier than it probably needs to be, just so I have some room between them. And y equals x squared. So my base is this region in here. Just put a few lines in there. That's the base of my thing. It's just like a little crescent shape. And then this thing rises up out of that. So sort of picture yourself looking at this from above. That's the ground floor of this solid. And the way this thing is built is that cross sections perpendicular to the x-axis. So if I slice up and down perpendicular to the x-axis, all of those slices are squares. I'm going to do a really crummy job here of drawing in 3D. So I'm going to do this kind of lightly. We'll use this little orange. So like here's a square that, or a base that has some length, and there's its little square. And then this one's going to be a little bit bigger. So its square comes up this way. And then at some point they're the furthest apart, and that's your tallest height for this thing. And then they start getting shorter again until finally you're down to squares that have height of 0. So you've got this weird thing with a curvy edge on one side and a flat edge on the other side, and they get taller in the middle and then gets smaller at the end. So it's kind of going up here and back down. Does that kind of make sense? What that solid might look like? It's kind
Can
of
you explain it again briefly, please, and thank you.
So no problem. So the and see, this is why you know what? I'm gonna try to undo, because I did a really crummy job on those. Oh, don't make me do that. Okay, didn't like that. Here's my problem. I started out okay. I'm gonna just, yeah. So this is a side to a square. And notice that this line, this one right here, the bottom, so the right side in that sort of square that's supposed to be looking like it's coming out of the page, the one that goes between the two curves, that's the base of the square. So I'm going to just draw all those bases first. So here's another base of a square. Here's another base of a square. Here's another base of a square. Here's another base. So then they get really tiny at the ends.
Those aren't the sides of the square?
Though, yeah, those are one side, or the base of the square, if you want to think of it that way.
And are we taking?
So that's one of the sides of the square.
Okay.
And the square sticks out of the page. So then this square, this comes up out of the page. So I'll draw those with little dashed lines. This comes up out of the page.
So it's like 3D?
Yeah, you're making a 3D object
Okay.
by having all of those slices perpendicular to the base are square. So that little wedge is just the base of this thing. You know what? This one is such a weird one. If you go with me on this one, we're going to finish setting this up. but I'm going to show you the next one, and I think it'll be easier for you to visualize because the shape is actually something you know. Okay?
Okay. Yep.
All right, so hang with me on this. This one's hard to visualize because we can't necessarily picture exactly what it is right now. Okay, so the idea now is that if we were to slice this thing, so if you were to chop this solid thing, it doesn't really have a name. You know, think about chopping, say, the pyramid that we talked about before, and you said the cross sections were going to be triangles. Well, we know that the cross sections, when we slice through this thing, are going to be squares because they told us they were, right? So what's the area of a square? How do you get the area of a square? Grab my chat back. Yeah, kind of, Curtis. It's kind of oval, but not completely. And yes, Aaron, I think somebody answered that for you. They will have the same answer if you go vertically or horizontally. So area of a square is, if I just have a square and all of its sides are the same, how do you get the area of the square?
Base times height, right?
Base times height. So in this case, it's side squared, right? Because the base and height happen to be the same.
Yeah.
Okay, so if we know the side length for these squares in terms of x, we can get this area function. So that's our next goal, to get area in terms of x. Well, what does the side length look like? It goes from the line to the curve. So the equation for a side is something minus something. X minus x squared. Top curve minus bottom curve. So this is a side right here. Kind of scribble on it over and over. And that fat line, no matter where I draw it, this one, this one, this one, those all have length of whatever the x value is minus the x value squared. So x is at the top, x squared is at the bottom. Yes, s squared. So a in terms of x would be x minus x squared squared. So that's our area function. Now we want to figure out volume. How do we get volume? We multiply area by
3/4, right?
by what?
3/4.
3/4?
Maybe not.
I'm trying to remember, think about where you got 3/4.
Maybe I'm thinking of like, I don't know.
Okay, just think in general. So if you have something and you now have the area of its base, or and then it's got some thickness. So in other words, just let's try to get the volume of one of these things. How could we describe its thickness? If it's, I mean, the whole thing goes from 0, 0 to 1, 1, right? That's where those guys cross. So each of these little squares that we're sort of thinking about has a thickness that's just a change in x or a little dx. Yeah, so it's the thickness is really like the height of the square. And so we can write our volume for one of these things is x minus x squared times delta x. or x minus x squared times dx. But this is just 1. And how do we get the whole volume? We add them all up. So we sum up all of the x minus x squared delta x's. And in theory, we do x sub k's here, and we let k go from 1 to n. And then we take the limit as n goes to infinity, and we've got another one of those Riemann sums. So x squared squared, oops, area, I missed my 2 here. Very important 2. And so my volume is the integral of x minus x squared squared dx from 0 to 1. And the general look at this is that this function is the area function. So that's really kind of cool, because it means we can calculate volume by integrating area, just like we calculated area by integrating the height or the length of the rectangle. So it's just sort of moving the whole area problem up 1 dimension. And that means that if we have an area function in there that we know, which we can get a lot of different ways. Right now we're doing this by slicing. We should be able to integrate that area function and then come up with the volume of the whole thing.
I have a quick question.
Sure. Is this Gabe?
Yep.
Just check. Okay.
So it doesn't matter where you write the upper and lower limits, whether it's on the right or the left of the integral, right?
The right or the, oh, you mean where my 0 and 1 are to the left of my squiggly sign?
Yeah.
Yeah, you mean,
Matter, does
so
it?
like, for example, if I had put the 0 over, I'll just go ahead and write another one. I can erase it. So if I had put the 0 here and the 1 here.
Yeah.
No, it's just notation. I just did them where
Reference?
I had space. I mean,
Okay.
some people put them totally below and above. Theoretically, they go to the right or above and below. I just didn't have room in there.
Okay. So, and then
But as
also,
long as I can see one's lower and one's upper, I'm good.
also for that limit arrow, is that supposed to be like pointing to like going down the next like row?
So no, I just meant we're going to take the limit. I
Oh,
should have
okay.
just written it in words. So take
Gotcha.
the limit as n goes to infinity. And that gives us, yes, and that gives us the next row, which is the integral.
Sounds good.
Yes, so truly the arrow belonged there. And then you could evaluate that. However, it's not a very difficult integral to evaluate, so I'm not going to use our time on that. Okay, I'm going to let us do another one, because I promised we'd do one where you could see the visual a little bit more easily. So let's take, not that one because it's very similar, number 3. So this one has the base enclosed by a circle. Okay, so this seems a little bit more easy to visualize. So we've got the circle x squared plus y squared equals 1, which is just our nice unit circle. And cross sections are a variety of things. So the first one, cross sections are semicircles. So I'm gonna kind of plop this up here and we'll use orange again. So if I'm saying cross sections are semicircles, this is where I fall apart and don't draw very well. But actually picture this, if these cross sections are semicircles, what is this thing? If everything I chop through and get is a semicircle, what have we got?
Piecewise?
Say that again?
Is it? I think I'm wrong. What, piecewise maybe?
Oh, no. I'm just thinking, what shape is this solid? So you've got a circular base and everything you chop through, every time you chop through, you get a semicircle. What is this thing? What does it look like?
Would it look like a dome?
It does. It looks like a dome. And it's even more than just being a dome.
What, just half of a sphere?
It's half of a sphere. That's right. It's a hemisphere. So we're really just trying to find the volume of a hemisphere. Now, the others, we're not looking at hemispheres. They're going to be a little bit messier. So we've got cross sections that are squares, cross sections that are equilateral triangles, isosceles right triangles with a hypotenuse in the base. So lots of different ways we can look at this thing, and the shape will change a little bit. But this whole idea about volume for slices is going to be that if we can figure out, and I'll do these in the right spot this time, integral from A to B. So we've got our limits of integration, and then we need our area function, and we're going to integrate our area function with respect to x. So on every one of these problems, A through E, what will our limits be for this problem, for each of these guys?
From B to A?
So A to B, what are my lower and upper limits? What are the endpoints there?
Oh.
This is the circle x squared plus y squared equals 1.
Oh, endpoints are 1 and 1, I think. Wait.
1 is one of them. That's the upper one. And the lower one?
-1.
-1. Yeah, that's the unit circle. So endpoints here are 1, 0, and -1, 0. Okay, so our job then is to come up with this area function for each of these problems. Once we do that, we can set up the integral pretty nicely. We're just going to integrate area, whatever it is, with respect to x from -1 to 1. So in this picture, I've got semicircles. So I'm going to just draw one of these semicircles. And remember, the thickness of these guys is the dx. So that's where that's coming into play. And the area piece is going to be based on the shape. So I need to know the formula for the area of a semicircle. Let's see. For a circle, it's pi radius squared, right?
R squared divided by 2.
Divided by 2. So what I need to know is, what does r look like in terms of x? Let's see if I can draw an r on here. There's the radius. The radius is that much. And I need the radius in terms of x. So it would be nice if I had an equation like I did last time for the top half of this curve, because that would tell me how high that is. How could I get an equation for the top half of that curve?
You could just set it equal to y, couldn't you?
Set it equal to y. So I'm going to solve this thing for y. So y squared is 1 minus x squared. And the top half will be the positive square root of 1 minus x squared. Notice the bottom half of this thing. Use a different color. We'll use the purple here. The bottom half of this thing is y equals negative square root 1 minus x squared. I don't need that just yet. Okay, so we know what the radius is. The radius of this semicircle is square root of 1 minus x squared. And we said we wanted to integrate area pi times radius 1 minus x squared squared over 2 with respect to x from -1 to 1. And that should do the trick. If you're going to integrate by hand, it's probably easier to pull the pi over 2 out. Notice how nicely that square root goes away, and you get a fairly simple integral that you can finish up.
Why is there a negative on the y equals negative of the square root of 1 minus x squared?
The negative sign inside the square root?
No, on the outside of it.
Oh, you mean the purple one?
Yeah.
That was an or. So
Oh.
remember, there are actually two equations there when you
Yeah, you're
solve
right.
for y.
Yeah,
You
you're
got the
right.
top half of the circle and the bottom half of the circle.
Okay.
We didn't need the bottom half of the circle for this one. Right?
Right.
We only needed the top half because we needed the radius of that semicircle.
We need the pause.
So we didn't need both of them. Had we used the negative square root equation, it still would have worked because we would have taken the negative and squared it and gotten the positive. So you'd have had the minus sign inside here. I'm going to put it in there and then I'm going to take it out. It would have been there. You would have squared it and you would have gotten the same thing.
Okay.
I'm going to kill that. Okay, so we're gonna do one more of these. I think that's about what we have time for. One
Wait, can
more
you do that up
setup.
there?
Again, I believe you guys can evaluate that integral, right?
Yeah, we leave it up there for like one more second though.
Yeah, I'm not gonna scooch very far anyway because we're essentially using the very same picture.
Oh, okay. You can move it. We're good. I finished.
Okay, let's see. So squares. So I'm gonna just put a little line here because that one's all set up. So for our squares, now this is the piece. And we already said for a square, area is side squared. And the side is the orange piece that we had from before. That thing. Let's pointer at it. This thing is the side. So the side goes from the top half of the circle to the bottom half of the circle. You see that? Top half to bottom half is the side of the square. Now, you could start from scratch, but I believe in sort of working with what we have, and we just did a lot of work on the last problem. Tell me how the side of the square compares to the radius of the circle.
Because that's the diameter.
It's the diameter, so it's double the radius, right? The side is 2 times the square root of 1 minus x squared. You could also get that by taking red function minus purple function. If you took red minus purple, top minus bottom, you would also get 2 times square root 1 minus x squared. So side squared is, oops, I want to go back to orange, is 4, square the 2, and then square the square root times 1 minus x squared. So there's my area function. And volume is integral from -1 to 1 of my area function, 4 times 1 minus x squared dx.
And that dx you drew on the graph right there, is that
That's the thickness of the slice.
can you look?
So
Can you
that's
show us
just
where
the
that is
change in
again?
x from here to here, or the little change in x.
Okay,
as
so
we
it's the
move
purple
along.
part.
So it's not necessarily, so I should really probably draw that along the axis. It's just that my drawing gets too crunchy. So it's just
that-
your little change in x along the x-axis
Okay.
as you move from -1 to 1.
Oh, okay. Gotcha.
So it's truly the thickness of each one of those slices.
So it's the
So
horizontal
in
change.
this case, we're slicing these little wedges that have different shapes.
Okay.
Okay. I think we won't do any more, but I'm gonna put this up for you guys so you can try this before next time, and then we can go through one or two of the other three, because the triangles maybe pose a little bit more of a problem. But keep in mind that the area of a triangle in general, any triangle, so I'm just gonna draw a funky, bad looking triangle. A triangle in general has area, I can't get rid of just part of that. There we go. Has area what? Let's see.
Times 1/2.
Yeah. Base times height times 1/2. So height, base. So in C, you're looking at equilateral triangles. In D, isosceles right triangles. So 45, 45, 90s for those. But we'll look at those next time, because we're at 11:50 and you guys might have class to get to at noon, and I do too. So we'll try to always end by now. Okay, any last minute questions? I am
The
going
test?
to-
When are those going to be?
So, oh,
I said I
okay,
missed.
did you go through the syllabus stuff?
I have not yet. No, I can if
Okay,
that. easier
take a
for you.
peek at it.
Okay.
There are tests that are in Newton Alta, and then
Okay.
there's a midterm, and then there's a midterm and a final.
Okay.
So
Do we-
they'll be around midterm time and final time. And then the first test, I think, is due the 13th of September.
Do you do
And that'll
quizzes?
just be over like half of the first chapter.
Okay.
It's truly just over area and volume. So we didn't
Got
do
it.
everything from that, but we've got a few more things to do. We're going to look at volumes of surfaces of revolution next time.
Do you do quizzes?
Do I do quizzes? You know what? I have done quizzes over the years, but I actually haven't in quite a while. I don't know. I'm not extremely fond of quizzes. If I were doing a face-to-face class, I might do hand-in homework, where you hand in paper homework each week or so. But I don't usually do like weekly quizzes. So you have your online homework, you have your online tests, and then you have a midterm and a final. That's the plan for the semester.
Sounds good. Thank you.
Okay, you're welcome. Yeah, go back and take a peek at the syllabus and read through the announcements on the main page in e-learning, and then make sure you get started in Newton Alta if you haven't done so already. It looked like most of you were in there. So once everybody's in there, you can get started and start working, and then holler when you have questions. And we will do as many problems from those as you guys ask during class. So if you don't ask questions, then I will try to not lecture too much. I feel like I lectured too much today, but I also feel like you guys hadn't had a chance to get much work into the problems where you would have had questions to ask me anyway. So sort of flip things around today. All right, any questions? All right, I am going to end us here, and I will not see you until next Wednesday, though, because today is the 2nd, Monday is Labor Day, and we're going to take the day off.
Sounds good.
Okay.
Thank you.
All right, have a nice, safe weekend.
You too. Bye.
Yeah, bye-bye.
Thank you. Bye.
Yeah.